Welcome to The Explainer. Today, we're going to crack open the very heart of the atom. We're talking about the immense, almost unimaginable power locked deep inside the atomic nucleus. All right, let's kick things off with a fact that's, well, it's kind of hard to get your head around. Atoms. You know, the building blocks of literally everything are almost entirely empty space. Picture this. If an atom were the size of a classroom, its nucleus would be like a single pinhead just floating right there in the center. That's it. But here's the crazy part. That tiny, tiny pinhead, it contains more than 99.9% of the atom's total mass. I mean, all the weight is crammed into that minuscule core. So that just begs the question, right? How can something so ridiculously small be so unbelievably massive and powerful? Okay, let's dive in and really unpack what's going on inside what is basically the densest object we know of. So to get to the bottom of this incredible power, we've got to start with the basics. Let's look at the anatomy of the nucleus itself, what it's actually made of. And you know what? It's a surprisingly simple recipe. You've only got two main ingredients. First, you've got protons, which have a positive electric charge, and then you've got neutrons, which, just like the name says, are neutral, no charge at all. And together, scientists just call them nucleons. Now, physicists love their shorthand. And for the nucleus, it's super straightforward. The atomic number, they call it Z. That's just the number of protons. And that is what defines what an element is. Then you have N, which is, you guessed it, the number of neutrons. And A, the mass number, is just the two added together. Simple as that. Okay, so here's where it gets really cool. You can't mess with the number of protons without changing the element completely. But the neutrons, you can change the number of neutrons. And when you do, you create different versions, kind of like different flavors of the same element. We call these isotopes. And hydrogen is the perfect example of this. Regular hydrogen has just one proton and 0 neutrons. But add a neutron and bam, you get deuterium. That's the stuff in heavy water. Add another neutron and you get tritium. They're all still hydrogen because they all have that one proton, they just weigh a little different. All right, so this brings us to a huge puzzle at the heart of the nucleus. I mean, we've got all these positive protons crammed into this impossibly tiny space. How on earth does that even work? No, really, stop and think about this. If you've ever played with magnets, you know that like charges push each other apart, right? They repel. So a nucleus packed with all these positive protons should just fly apart instantly. It should blow itself to pieces. So there has to be some other incredibly powerful force at play here. And of course there is. It's called the nuclear force, or sometimes the strong force. And believe me, it is strong. It's the most powerful of the 4 fundamental forces in nature. But here's the catch. It only works over crazy short distances, like the size of a nucleus, and that's it. Think of it like the universe's strongest superglue, but it only works if the pieces are practically touching. So where does this insane energy come from? Well, the secret lies right here, in probably the most famous equation in all of physics. What Einstein figured out was that mass and energy aren't really separate things. Nope, they're basically two sides of the same coin. You can actually turn one into the other. And this leads to something that is, well, it's just weird. If you take a proton and a neutron, you weigh them separately. Then you make them join together into a nucleus and weigh that. The nucleus will always weigh less than the sum of its parts. It's like some of the mass just, poof, vanished. This is what we call the mass defect. But here's the absolute key to everything. That missing mass, it didn't just disappear. Remember A equals mc squared? That mass was converted directly into a huge amount of energy. And that energy is the binding energy. It's the powerful cosmic glue we were talking about, the stuff that holds the entire nucleus together against all odds. So, this binding energy, that's the source of all nuclear power. And it turns out there are two main ways we can unlock it, either by splitting atoms apart or by smashing them together. Okay, so take a look at this. What's so fascinating here is that not all nuclei are created equal. The most stable, the most tightly bound nuclei are the ones in the middle, right around iron. They're at the peak of the chart. The really light ones and the really heavy ones, they're much less stable. And that gives us two ways to release energy. You can take a really heavy nucleus and split it to move towards the middle, or you can take really light ones and join them together to climb up that hill to the stable peak. So let's put these two paths side by side. On one hand, you have fission. That's the process of splitting a heavy nucleus, like uranium, into smaller bits. On the other hand, you have fusion. That's the complete opposite. You're joining light nuclei, like hydrogen, to form a heavier one. One is what powers our nuclear reactors, and the other, well, that's what powers the sun. And the consequences of figuring all this out are, well, they're everywhere. This incredible nuclear power is what runs our universe, from the light of the most distant stars all the way down to the electricity powering your home right now. Think about our sun. Every single second, it fuses hundreds of millions of tons of hydrogen into helium. That tiny little bit of mass that gets lost in the process, it's converted into the sunlight and heat that makes all life on Earth possible. And it's been doing that for billions of years, and it's got billions more to go. And then, back here on Earth, we've pretty much mastered the other side of that coin, fission. Inside nuclear reactors, we're constantly splitting heavy uranium atoms, and just one of those splits releases millions of times more energy than any chemical reaction, like burning coal. That's how we generate these vast amounts of electricity. And that brings us to our final and maybe most important question. We've harnessed fission, right? The power that comes from splitting the atom apart. But can we now control fusion, the very same process that powers the sun and the stars? What you should really take away from this is the immense potential we're talking about, a clean, nearly limitless source of energy. But at the same time, you have to appreciate the monumental challenge of building and containing a star right here on planet Earth.